Welcome to week 14. We basically wrap up the course this week. As you know, next week it's exam, review, and then final exam. So this is kind of the end of the line, and this is not terribly challenging stuff. So the concept of graph theory, which is what we're going to be embarking on. It's the theory of how to draw a graph. Well, I learned that in basic algebra. Well, no, it's not exactly the same sort of thing. One of the simple models that some of you may have seen, and I've alluded to this before, in linear algebra, we talk about solving systems of equations, but of really specific types of applications. For example, one of my favorite ones is the traffic light problem. And we do this problem in my linear algebra class. This is on day 2. I do this problem. And the idea is I usually start with something simple like 4 intersections. There are cars coming into the intersection and then cars leaving the intersection, but they might be able to go in this sort of manner, okay? And maybe it looks something like this, and maybe something like this, and then here they're going that way, and here they're going that way, maybe. So it's something like this. Cars can come into this intersection from one direction, but can leave in 3. Cars can come to this intersection from 2 directions, but only leave in 1. Okay, cars can come into this intersection maybe from 1 direction and leave in 2. Cars can come in this intersection in 3 directions and leave in 1. This would be just a simple model. So then what you do is you'd say probably something like cars per hour. How many cars per hour can enter this intersection? Maybe it's 100, maybe it's 1,000. You come up with your numbers. These are the entries, these are the exits. The only rule is the same number of cars have to leave as come in. So this is often referred to as a sources and sink problem. It's kind of funny, the word sink, that's the part leaving, think like a sinkhole. So the source is what's coming in, the sink is what's leaving. So in a more advanced model, what you'd have, actually, think of it like a box. And I have one way into the box and one way out of the box. I don't know what's happening inside the box. There's a whole network of things going on. And again, this is often referred to as network analysis. It's a branch of graph theory, sources and sinks. The only rule is what goes in must come out. It can't somehow get trapped inside. There's no black holes for it to leave and things of that nature. And a lot of really advanced models are used using this simple reasoning. So in linear algebra, we study this problem. Okay, and we have a system of equations and there's no unique solution. But if it's a traffic flow problem, there will be a finite number of solutions because there's a finite number of cars and I can only have discrete solutions. I can have 5 cars leave, but I can't have 5.7 cars leave. Yes, I can have 5 cars, I can have 6 cars, there's no value in between. If this is water and I'm doing something, or electric current, which is also a similar problem, oh, then it's not discrete, then it's continuous. I can have decimal values. That's a much different problem. So in a sources and sink problem, we usually think about it as being a finite problem, but there are a lot of possible answers. And so the idea is not so much as what is the answer, but really how do you set up the model? So this is a really low level example of graph theory. And again, in a linear algebra class, I would hope that you got to do something like this. And in my class, it's day 2 because it's section 1.3 of Larson. So it's not something that's considered advanced. But the bigger picture is in a sources and sink model, you can mess around and do all sorts of things. You can make it as complicated as you want, just following some of the basic axioms of, again, graph theory and in this case, network analysis. There's a problem that we're going to look at next day. It's a very, very classic problem. It's called the 7 bridges of Cronusberg. Some of you may have heard this. There's a place in Germany where there's a bunch of little, I don't want to call them rivers, they're probably more like streams, but technically they're called rivers. And then there's bridges over these rivers. There's several of them, 7. And the question is always, can I cross all of the bridges without ever backtracking and crossing a bridge twice? And it's a very classic mathematics problem. And it's illustrated, I believe it's section 10.2 of the 4th edition, 10.1 of the 5th edition. I have to check because I can't find my 4th edition. And it's one of these classic problems that say, is it possible for me to go visit and cross all the bridges exactly one time? Because that seems like a simple enough question. And we're going to attack some of these basic ideas. And then the last one is the last one I want to introduce as a possible problem is sometimes this is referred to as they used to call it the telephone line problem when I was in school. And I have houses, let's say something like this. And what I want to do is connect a telephone line to every other house. Okay, so the telephone lines usually are up in the air, but now they can be underground. Or basically I can just do like we did with kids, you have 2 tin cans and a string, and I want to connect it to everybody. So this guy's connected to here, and he's connected to here, and he's connected here, and he's okay, great. And I can do that's legal. Okay. Is it possible for every person to connect to everybody else and not cross paths? That's another interesting question. Is it possible? And that actually turns out to be an extremely important result that we use in higher levels, but we're going to introduce something that simple. Again, this is all part of graph theory. So let's start with some very basic definitions. In graph theory, you have 2 things going on. You have put this little point here, it's called a vertex. And if I have a second vertex, then I have something connecting them. And this thing is called an edge. So you have vertices, you have edges. There's not a whole lot else going on. And it's the description and in many cases the count that we are interested in. So if I called this vertex V1 and I called this vertex V2, let's call this edge E1, assuming we're going to have more edges, then we would actually say E1 is equal to, and we write it like this. We write it as a set of the vertices that it connects. Now, usually edges are directed, usually. So I'm starting at V1 and I'm ending at V2, because the idea eventually we're going to have paths. And there's a whole lot of terminology. If you're a hiker, somebody goes on hikes, you have paths, you have trails, you'll go on a walk. And if you complete an entire loop and come back to the start, sometimes you might refer to that as a circuit. Well, we actually use exactly the same words in this case. We're going to introduce all of those next time. So a lot of the vocabulary we use in this scenario is just everyday English that makes perfect sense to us. Excuse me. Now, I can have more than one edge. See, I could also do this. That can be a second edge, and there's nothing wrong with that. Ooh. So a vertex, by the way, doesn't have to have any edges. A vertex can just stand alone. It's kind of boring. So sort of like on an island with no bridges to get to the island. So one of the things right off the bat we want to discuss is basically how many vertices or the degree of a vertex. So we're going to define degree, which is a really important term. Degree of a vertex is simply the number of edges connected to, let's say it that way. So an easy way of thinking about this is, if I've got several vertices, let's say, and I have a path here, and I have a path here, and I have a path here, and maybe I have another path here, and maybe I have another path here, I'm just crazy wild. Then if I'm looking at this vertex, how many paths are leaving it? Okay, well, the easiest way to do it is don't look at the other vertices. I like to do it like this. Just I'm going to draw a little circle around it. How many distinct little things did I cross? Well, there's 1, there's 2, there's 3, there's 4, there's 5. There's 5 little directions leaving that vertex. Where they're going is irrelevant. It's how many are leaving. So if this is V1, then we'd say the degree of V1 is 5. That's simple. Okay, so let's call that V1, let's call that V2, let's call that V3, and let's call that V4. This is not a calculation, this is a count. Okay, so anybody, V2, what would be the degree of V2? And by the way, the arrows really aren't important when it comes to degree. Okay, the arrows aren't important in terms of degree at all. Anybody want to just blurt out? What do you think V2 is? There's my V2. What would be the degree of V2?
1.
1. Yeah, kind of boring. How about V3 and V4? Anybody want to try those?
V3 would be 2 and V4 would be 2 as well.
Good. Now, I want you to notice something. If I add up those degrees, it adds up to 10. Okay. Why is that interesting? Because an edge must always be associated with two vertices. So a really simple and absolute, and one of the more important theorems of every possible thing we're going to do in graph theory is that the total degree of this, and by the way, this is called a graph. I've got vertices and edges. This thing is called a graph. It's that simple. The degree of a graph is the sum of the degrees of all the vertices. That makes sense if you think about it. How many edges do I have in this graph, by the way? How many edges? That's not hard, right? Let's just start with that. 1, 2, 3, 4, 5. Everybody agree with that? I have 5 edges. But you notice the total degree is 10. Is that a coincidence that the total degree is exactly 2 times 5? Or do you think that's some kind of rule? Think about this for a moment. If an edge has to connect 2 vertices, then shouldn't there be exactly twice as many vertices as there are edges, or twice as many edges as there are vertices, or twice as many? Where's the 2 in there? If one edge has to connect 2 vertices, well, I had 4 vertices. So 10 didn't come from that. 10 came from the fact that if I add the degree of each vertex, that's how many. So if there's for example, let's start it. This guy right here connects 2 different vertices. So this edge is really counted twice when I'm counting degrees, because it counts as a degree for this vertex and it counts for a degree for this vertex. Every edge, because it's joining 2 vertices, is going to be counted in both of those vertices degrees. That's probably a simpler way of thinking about it. So that means quite simply that the degree of the graph should always be double the number of edges, which means that the degree of a graph is always even. That's kind of an interesting concept. So what if, excuse me, what if I have a graph and it's got a vertex and nothing else? This is like the most boring graph there is. What would the degree of that vertex be?
Would it just be 0?
It would be 0 because there are no edges. Okay, let's put a second vertex out here. And right now, that's all I have. I have just 2 vertices. I have 2 islands in the middle of the Pacific with no bridges or ways of getting them. Well, now they both have degree 0. Well, that's kind of boring too. Now let's connect them. Okay, now this one has degree 1. Now this one has degree 1. So the total degree of this graph now became 2. Okay, let's do another one. There. Now this one has degree 2 and this one has degree 2. I could do this all day, but every time I add an edge, each of the vertices. Now an edge, there's no such thing as an edge that just dangles in space. That's not an edge. It's just hanging out there with no vertex at the other end. No. Now there is one odd one. I can do this. Let me have vertex 3 out here. I want vertex 3 to have an edge, but I don't want it to connect the vertexes 1 or 2. How would I have an edge that doesn't connect to another vertex? It comes back to itself. That is called a loop. So if I'm looking at the vertex, and now this is where it can be a little confusing. There's only one edge and there's only one vertex. But remember I said earlier, draw a circle. If I draw a little circle around my vertex, you see 2 very distinct paths here, one here and one here. So the degree of this vertex would still be 2. Now that's one that kind of confuses people, but let's say you're leaving your house and there's a loop around your neighborhood. Maybe there's a park and there's a loop and the loop comes back to your house, but you can start the loop by going that way, or you can start the loop by going that way. And you have 2 completely different directions. You have 2 completely different paths. You're not retracing your footsteps, but in the end, you ended up at the beginning. So even though you say, well, it's coming back to itself, there's nothing wrong with that. That'd be kind of like saying, I'm going to go here and come back this way. I can always come back to myself in that manner. So a loop will count twice in a sense for degree. So that's not supposed to be complicated. So this is now there's two types of graph. This is a graph. This is a graph. I didn't give you any directions. Now let me put little arrows. The arrows means that's the only way you can go. Well, not necessarily, but that's the way you can go. Now this is called a directed graph. Now this is kind of boring because not all graphs are directed, but a directed graph, we give it a little nickname. So you will see something in the reading called a digraph. Now that's confusing because the prefix di means what? Anybody know? The prefix di means exactly.
Two?
It means two. Oh, that's not two. That's a shortening of directed. And I have to point that out because if I saw a digraph, I'd think, oh, two graphs. Okay. Most English words that start with di means to dissect. Oh, okay. Hydrogen dioxide. Yeah. When you see di, especially in chemistry, when you see di, that means two of something. Doesn't mean two in this case. Di is just short for directed. I don't think that was a good abbreviation, but it is. So there's a graph, there's a digraph. It doesn't change how you do things. But what it would mean is that I can't go down this path. So think of a digraph quite simply. If this was traffic, a digraph would mean I might have one-way streets. Oh, okay. Now, if this represents a street, this would be a street that has a lane in each direction, which is what most streets would be. So I can easily represent traffic flow. The fact that I drew this curvy is irrelevant. Oh, okay. This is I'm on the right side of the street, and then this is the other, or it's just backwards. I have a street and I'm going both ways. So now we have vertices, we have graphs, we have loops. Okay, and counting the degree is easy. So here's what I'd like you to do. This is a simple exercise. I would like you to draw for me a graph. Let's keep it really simple with 3 vertices. And they will be of degree, how about 2, 2, and 4. I want you to draw a graph with 3 vertices of degree 2, 2, and 4. Now, I want to point something out. If I said, okay, I'm going to draw you a graph. Here's a vertex, and here's my edge. Now, somebody else draws a graph, vertex, vertex, edge. Somebody else draws a graph, vertex, vertex, edge. Are these graphs different or are they the same? That's not a trick question. Are they different or are they the same? Want to try that?
Same.
They're exactly the same. I have 2 vertices connected by an edge. How I choose to orient them, left, right, up, down. Heck, I could make it coming towards you. It doesn't change anything. That's an oddity. Now that I'll explain where that comes from. That's a whole nother branch of mathematics in and of itself. All of these are the same graph. That means that if you have a right answer and your neighbor has a right answer, your graphs may look completely different, but you've represented the same thing. Thinking, point A and point B, and there was one way to go. Now, I don't want a directed graph. I just want a graph. So everyone try this for a moment, and let's see if we can come up with something. I'm not even going to ask you for your result, but I just want you to try just to see, what does it feel like? I think the easiest thing to do is just start by drawing your 3 vertices. By the way, your 3 vertices can be on a line. They don't have to be separate by any stretch, but it's probably easier to conceptualize them if you don't make them on the same line. Okay, well, if this guy's going to have, let's say the first one's going to have degree 2. Okay. Well, that was easy enough. And let's say this one's going to have degree 2. Is this legal? Yes or no? Just yell it out. Is that going to work?
Yes.
For 2, but I count both of those pieces, don't I?
So it will be 3, not 2.
So good. Right now we're at 3, so that's not going to work. If I'm trying to get 2, well, the easiest way to get 2 would either be go back to this one or just go to this one. All right, now I've got all of them with 2. How the heck am I going to get 4? Well, if I do that and I do that, let me ask you, okay? If I do this and this, that'll work. Now that has 4. Will that work?
No,
Because
because it has to go both ways. It's not just one.
well, there's no arrows. This is not directed. Why? That one now has 4. If I add those 2, but why won't it not work? The other ones that now have 3. Oh my goodness, this isn't as trivial as you thought. There's exactly one way I can proceed from here.
Loop.
One of them is going to have what?
Loop. A loop. We
A
need to
loop.
make a loop.
It doesn't matter which one. Let's say it's this one. Now I've got 2, 2, 1, 2, 3, 4. Okay. So is this the only way I could do this? No. This is probably the simplest way. Now I'm gonna show you a completely different one. By the way, putting them on a line. Can I have the exact same graph if I put them on a line? See this here? I can put my loop, maybe I put my loop here. It's the same graph. How could it be the same graph? Because I can bend and twist this and I would get this. You know, just pull this point, just pull this guy down to here. Now it's the same picture. So, but you made that one curvy. It doesn't matter. It's still an edge, whether it's curvy or straight. Oh, now that's not the only version though. Now I'd like you to think, can I draw a complete, I'm gonna put my 3 points right here. Can I draw a very, very different 2, 2, and 4? Now I want you to think about this because I'm gonna have you verbally describe it to me. These are the same graph. Again, in a sense, they're the same graph because if I did this, this is the same graph. You know, think of your edges as being very elastic. So I just stretched it out a bit. It's still an edge joining these two. These are exactly the same graph. Okay. Don't think about straight versus curve. Think about connecting. Can I draw a very, very different version of this? Well, there's my 2 and my 2.
Now do that again, connecting 2 other vertices.
Well, I just don't have these 3 though, remember. So if I connect these guys, what's the problem? If I connect them, 1, 2,
3.
I'm still trying to stick with that.
So you'll do 2 loops.
2 loops. Now you're thinking creatively. Oh my goodness, that's crazy. But these are completely separate because there was no way to get from that vertex to these vertices. So if I thought of these as roads, you know, this is my house, here's a road, there's another road, but I can't get there. Or, you know, it's an island. These are completely different graphs. Okay, now if I can bend and twist, let me ask you a question. Look at this graph for a moment. Now I'm going to remove that loop. Now I'm going to put that loop here. Is this a different graph from the one I just had? Or is it exactly the same?
It will be 2, 4, 2, right?
The one I had a loop here and I removed it and I put it here. Is this a different graph or is it
It
the
will
same?
have different degrees, right?
2, 2, 4.
Wouldn't it be different because it's a different vertex? I mean vertex.
Okay, now I'm going to remove it and I'm going to put it here. I've just done you 3 graphs. I've done one with the loop here, I did one with the loop here, and I did one with the loop here. Are those all different? They actually have to either be all different or all the same. Remember I said you
I'd
could
say they're
bend-
not different.
I'm sorry?
I don't think they're different.
They are the same. Think of it really simply. If I just take this and I rotate it, oh, aren't I just moving the loop down here if I rotate it? And if I continue rotating it, do you see that if I just simply rotate that shape, I'm moving the loop around? That's one way. That's an easy way of thinking about it. But in this case, there's nothing I can do here that would ever make it look like this. Now, this, this is a totally separate branch of mathematics. It's sort of like combinatorics on steroids in multiple dimensions that is abstract and all this. This is from something called topology. Topology is a very, very abstract branch of mathematics that's absolutely essential. It's largely geometry, but it's not Euclidean versus non-Euclidean geometry, if you know what that means. It's something simpler. If I took a basic shape, let me take this. Hold on. I'm going to take, now, right now I have a lid on, so this can be considered basically a solid shape. I can mold this, I can shape this, I can make this, think of it as like it's clay. I can make it into something else. I could make this into a bowl. Okay. They would be topologically equivalent if I can form another shape from this one. Now, I'm saying think of the solid bottle, don't think of this. Now look at this loop. This is different. I now have a loop in there. I can't lose the loop because think of the loop as kind of like a hole right there. I can't lose the loop. Oh, so now if I could form and reshape this, I could make this into a coffee mug because of the handle. And you say, well, what about the insert? Yeah, but there's no way out, like a bowl. The bowl and the solid rock are the same thing topologically, but this one has a hole. So this is topologically equivalent to something called a torus, a donut. I can bend and form and shape this, but everything that I shape this in still has to have a hole. I can't lose or gain another hole. So I know it's like, that's what it means to be topologically equivalent. Okay. Joseph, you have a question?
Yes, I have a question about the problem we just did. Is there not a third solution?
Oh, there might be. What would the third solution be?
Maybe just draw three vertices in one line. And then from the center vertice, you draw two edges to each of the outer lines.
Would that work, everybody? Yay or nay?
Yes.
Yeah. I didn't, by the way, I didn't say this was the only other solution. I just said this was a different solution. Now, is this different or is this the same from what we've done? No, there's no loop in this one. So this is definitely different from this one. This has a loop clear. And by the way, I did one a moment ago like this, and we did the same thing, but I remember I put a loop there. And I think I then, I connected these two, or you could, any which way. This and this are exactly the same because I could bend and twist and stuff, but see that loop? I'm not losing the loop. This has no loop. So these two are identical. This is different. So we've come up with three completely different and valid solutions. Now a question might be, how many solutions are there? That's actually really not that important, believe it or not, because if I start worrying about how many solutions, what happens if you've got, 100 vertices? Yeah, it starts getting way too complicated if you start worrying about how many. You just want to know, is there a solution? And now, how do you know there's a solution to this problem before you even started? Can anybody tell me how you knew that there was at least one viable solution? This is the most important part of all. How did I know there was a viable solution? There's one thing and one thing only that told me that.
The graph, the degree of the graph is always even.
Yeah, the sum of those three numbers was even. Those numbers do not all have to be even. No. I can have odd degrees all over the place. I can have odd degrees. Odd degrees are not an issue. In fact, let's do that one next. The mistake some folks make is they say, oh, as long as all the degrees are even, you're good to go. Okay, I'd like you to now draw, let's do a new problem. Let's do, let's keep it simple. I want you to do 4 vertices, and I want the degrees to be 1, 1, 3, and 3. Ooh. First of all, is that possible? You're going, I hope so. Well, let's do it. And again, to make it easier, I'm not going to put them on the same line. It is absolutely correct to put them on the same line, but sometimes it's harder to see a viable solution. So I need to create a scenario. Now, there we go. All right. That's a good starting point. Now, the thing is, I'm going to leave these guys alone because I need the ones. So if I have any other edges coming out of either one of these, they won't be 1 anymore. So I need these guys to now be 3. How am I going to do that? I want to try that one.
A loop on 2 of them.
I could do a loop. I could do a loop. Now, everyone stare at that for a moment. Is this viable? Does this work? Yes or no? Does that work?
Yeah.
The person who offered it said yes. I'd like to, does anybody else agree that this works?
Yes, I do, because we did create two vertices with degree 1.
Now, let's do a different one. Now, this is interesting. These are two completely separate graphs. No way around it. They're two separate graphs. I would like a graph where you can get from one vertex to another. See, right now, you cannot get from these two vertices to these two vertices. I would like a graph that I can get from any one vertex to another. And that we call a connected graph, which makes perfect sense. If I can always get from one vertex to another, there is a road, there is a path to get there. So we'll do the same thing. And just let's keep these as the ones just to make it easier on ourselves. Would this work? Now I have a connected graph, but these are only of degree 2. What can I do?
You had another one on the top.
Another edge. Oh, now that will work. Again, remember I said think circle. 3, 3, 1, 1. Okay, very different. These are not equivalent graphs. They are not the same thing. Now, if I put all of them in a line, I could, so let me give you a topologically equivalent graph to the first one, all in a line. Heck, I'll put it over here. This is topologically equivalent to this one, or I could put the loop over here. This one. Okay, clearly these are different. Clearly these are the same, because if I just said, well, let's take this and we'll just bend it down to here. We'll take this piece and we'll just bend it down to here. Another, back to the same thing. So if I can move it, it's the same. If I can rotate it, it's the same. It's not different. Okay. If we were in a geometry class and I was asking you if two shapes were congruent. Okay. Let me give you a really simple example, because you know the answer to this, but sometimes we're not thinking about it. Are these shapes congruent? Anybody? Are they congruent?
Yes.
I have two 2x6 rectangles, but this one's going sideways and that's off at an angle. Really? So that means if I take a textbook and I go like this, it's now a different textbook. If I go like this, no longer the same book. Simply moving something doesn't make it different. It just where it is might be different. But I think we all agree these are congruent. The fact that I rotated it a little bit doesn't mean anything. Okay. Now, how would I make it so that they were no longer congruent? I'd actually have to change the dimensions, wouldn't I? Then they would no longer be congruent. But simply moving it to a different spot. So in algebra and even in calculus, you could shift a graph. You're drawing a parabola. You shifted it left or right by taking x and replacing it with x minus h. You shifted it vertically by taking y and replacing it with y minus k. The graph looked exactly the same. You put it in a different place on the xy plane. So the graphs themselves would still be congruent, even though they were located somewhere else. And their equations, therefore, would look a little bit different. So this is the same thing here. So now we have the concept of edges, vertices, degrees. All of these things are good. Now, what if you got your neighbors over here, and you got your neighbors over here. And you would actually like, you know, we're in the future, you know, all the electricity has gone out. I think they made a show about that a few years ago, right? There's no more electricity, right? There's no more technology, but you want to communicate with your neighbors. So what you're going to do is everybody's going to get an empty tin can, and you're going to put a string. I don't know if you ever did this as kids. It actually really works well. Depends on the integrity of the string, but you can talk into the tin can, and the person at the other end can actually hear something what you're going to say because of the vibration. It's crazy physics, but I want to connect to each house on the other side. Okay, keep it really simple. I want to connect, and I'm not worried about the strings crossing. I'll just put some up in the air and some down on the ground. Okay. Oh my goodness, this is crazy. Yikes. So this is what I'd be looking at. This is what is called a bigraph, not a digraph. Now, bi always means two. There's never going to be short for something else. Essentially, what I did was I took the vertices on one side, I took the vertices on the other, and I connected the edges this way, but I did not connect them with each other. So in a sense, it's saying I'm going to take one set of vertices, connect them to another set of vertices, but not within the set of vertices. I don't care if they're connected or not. Okay, that's a very different kind of animal. So this is called a bigraph. So I'm going to back up because there's some notation going on here. If I gave you a simple set of vertices, this is a better looking graph than the other one. Every vertex is connected here. There's an edge joining every vertex. There's an edge joining every vertex. There's an edge joining every vertex. I think we all agree with that. This is called K2. This is called K3. This is called K4. K is actually short for Kuratowski, who was a mathematician, but don't worry about that. All right. I can keep going forever and ever and ever. The subscript refers to how many vertices, but every one of them is connected to every other one. So one of the first things we ask is, and by the way, you do notice that every vertex is joined by an edge, but none of these edges cross. I mean, all of these edges cross. None of these edges cross. Let's have some fun. I want you to take a moment. I want you to draw K5. And by the way, the orientation, I'm drawing them kind of like regular polygons. And the only reason is it's just easier to see. I could make all of these on the same line and it doesn't change anything. Okay, putting these four vertices linear and then just having things go around, that's totally okay. That's not a different graph. But the visual, I think, is easier if you're having your points looking more like a polygon, because in connecting them, it's a little more obvious. Can you draw K5 without any of the edges crossing? I want everyone to take just a moment to try that. Can you draw K5? Again, K5 means I'm going to do this. I'm going to do that for each vertex. Can I do this without them crossing? Oh my gosh, how am I going to get to here? Oh. How am I going to get to here? Oh, that's easy enough. So right now I've got those two. Is there an issue? Can I get these guys joined without crossing? Is there anything clever I can do? Stare at that for a moment. This guy, I can join him to here. He's already got there. He's already there. Everything's done except those are the last two that need to join. Go, well, what about these two? Well, no, they're joined here. That's the only one that hasn't been joined. Turns out It's not mathematically possible. Not if you're on the plane, by the way. If you're in 3D, that's different, but we're not in 3D, we're on the plane. I cannot connect those vertices. So this is, I'm going to tell you something. We're not going to use this, don't worry. If I have this in a larger graph, I can always connect the vertices. So we'd say if I had a graph that had K4 as part of my graph, I can always connect the vertices within there without any of the edges overlapping. But if my graph has a K5 in it, a subgraph. So in other words, if I try to do K6, K7, K8, K9, and so on, all of those would have K5 in them automatically. Okay, this is in here. In fact, it's in there several times. If you have K5 in your graph, that's called a subgraph, then it's not possible to connect the vertices. And by the way, this is a huge logistical problem in the real world. I say, think of things like telephone lines and stuff. So if you have a K5, you can't do it. Okay, if K5 is a subgraph, so anything that has larger than K5, clearly you can't do it. And that's a really cool thing. I remember learning this when I was in college. Going, oh, that's awesome. So therefore, you want to connect the lines across the street. Well, one thing about telephone lines, let's leave telephone lines. Telephone lines don't do well if they're crossing, because if they touch each other, that's bad. So now you have to have things at different heights. Oh, which kind of makes things messy visually. So a number of years ago, it's been many years, they started saying, what if we put the lines underground? Oh, then we can have different heights. And that makes it easier, but digging underground, that's not easy. It's costly. But if you think about your neighborhood, I have telephone poles outside. I live in a neighborhood that still has telephone lines and all the lines are still up in the air, but there are areas where all the lines are underground. So then as long as I have them at different elevations, then I don't have to, the crossing, they're called skew lines. They're not going to intersect. So that's kind of a cool thing. Now this guy here has a name that I just drew. I have 4 and I have 4 and I'm connecting them. This is a bigraph. This one is K44. So if I have a group connecting to another group, we indicate them completely different notation. Now, in the K graph, obviously, there's no way I could draw this without having things overlap. So let's start with a smaller bigraph. Let's do something really boring. K11. There's my K11. Well, I'm pretty sure all I got to do is do this. All right. K11, not an issue. Now I could do K21, I could do K12, I could do K27. That doesn't matter. So let's leave the numbers the same for a moment, just to make it easier on ourselves. What if I want K22? Okay. That means these two are connected to these two. That's all that matters. How do I get this guy to this guy? There. I've just drawn K22 and nothing crossed. Now let's go K33. And this is not really important, but generally the K here is a capital K, just so you won't confuse it with some other crazy notation. So I've got, that means I have 3 on each side. I want you to draw me a K33 and try not to make them cross if you can help it. Take a moment. Again, these don't have to be linear. But since I'm connecting to these sets, it's probably easier from an orientation standpoint if I make these linear and these linear, okay? So try that. This is how you do it, by the way. Actually, like this. Make that a little bigger. Hopefully everybody sees a problem with this. Can't draw that one, can I? Kind of enclosed. So it turns out K33 is another problem child. Okay. If K33, I cannot draw an edge from all of these vertices to these vertices without crossing an edge at some point. And we don't want to cross edges if we can avoid it. Again, I think of telephone lines and things like that. So it turns out any graph that has a K33 is a subgraph. We have an issue here. So the evil ones start at K5 for single or for a a bigraph or often referred to as bipartite. I hate that word, a bipartite graph. Some people just say bigraph. K33 is the problem child. And because of this, we can do bigger problems. I mentioned the 7 bridges of Cronusberg, that this comes from this sort of mathematics. So if I'm asking, can something be done? And I want you to think about bigger picture. Maybe you're downtown now and you have many, many streets and many, many intersections, and you're trying to do certain things. I have an idea in mind. Can it actually be done? Well, the mathematics, I just have to look at the graph theory and say, yes, there is a solution to this, or no, there is no unique solution to this. You can't get it done. No, it's an interesting problem. Okay, so this is just intro. One of the things I've asked you on the new quiz, by the way, I need to repost the quiz. I realized I'd sent the wrong copy, so don't start the next quiz yet. I actually have to update it. I'll send it out later. I just didn't have time. Being out of town, I was scrambling last night to post things, and I realized I posted a different version of the one that I wanted. It's only slightly different.
Wait, is this quiz 23 or quiz 24?
I might have to check them both. Definitely quiz 23, because I looked at one of the questions, oh, that's not the one I wanted. So hold off on that one. Give me a few minutes. I'm going to do it. 24 is probably okay. I think it was 23 was the one that I had. It was almost the same, but I had a different version. This happened on the last exam. I spent hours creating the perfect exam, but I gotta tell you, because of the union and the intersection symbols, I had to save it as a PDF and then load it. I had a previous version saved as the PDF. And what I do is I take every exam and I change every question on every exam, every semester in every class. I don't ever give the same exam twice. So I change every question. So what I do is I save the previous semester and then I just edit it. So I wrote the greatest exam 2 you've ever seen, and I saved it. The problem was I sent you guys a PDF version of the exam because some of your computers do not do well with the union and intersection symbols I found. It's really a strange thing. Those are the only 2 symbols that some of the computers cannot translate. So what I did was, after I got done with this perfect exam, I forgot to resave it as a PDF. So the saved PDF was last semester's exam. That's why when you got it, it said fall. I didn't say fall on it, because that was the original saved one that I edited as a regular document, but I sent you guys the PDF. There's only been a couple of times this semester where I sent you things saved as PDFs. And again, it was the whole union intersection thing. I don't think there's any of those on this test, so that's not going to be an issue. But yeah, it was kind of silly. So sometimes when I'm pulling things up, I'm pulling a saved version of something, but it's not the one I wanted because I have 2 versions. Yeah, it's crazy. Anyway, we're going to stop there because that's what I want you to see. You're going to find the problems are not challenging, but you definitely want to practice them because there's a lot of vocab involved, particularly in the next section. It's kind of funny. We're going to go for a walk, and is my walk going to be a circuit? Is it going to be a path? There's all these different words that we're throwing in there that actually should make perfect sense, even from an English standpoint. There's nothing challenging. Now, the next quiz, though, based on what you saw today, if I give you a question, I say, for example, draw a graph with these vertices, that should be an easy thing, but it means that no 2 people are probably going to have exactly the same picture. So I'm going to give you one more problem. I would like you to draw me a graph. Okay, draw me a graph where the degrees are, let's keep it simple, 2, 3, 4, and 4. I would like you to draw me a graph where the degrees of the vertices are 2, 3, 4, and 4. Okay, and you can't go home until you finish the graph, or at least you answer the question. So I tend to like to do this because it's easier for me to see. So I can go like this. I can go like that. I can go like that. Well, there's my 3. So there's a 2, and there's a 2. Oh, no, that's a 3. Oh, then I just need a 4. I'm now 2, 2, 3, and 3. So I need a 4. Well, I can go like this. So now, okay, now I'm 4, 3, 3, and 2. So I just need one more. Can I get another 4? If I take this 3 and I make it another 4, maybe by looping it there or looping it there, won't I be adding a degree to some other vertex? Can anybody tell me in simple English why this is actually impossible?
The total agrees uneven.
The degrees are not even. So you can go home if you can give me the reason why it can't be done. Otherwise, you're going to be trying and trying and trying. By the way, this sort of notion happens in real life all the time. This cannot be done, but people will spend a great deal of time trying to find it anyway. It cannot be done because the total degree of the graph we showed had to be even. Again, each edge has to be connecting to 2 vertices. You can't have an edge that only connects to one vertex. That's like having that dangling edge, like I said before. So this cannot be done because these do not add up to an even number. It's actually that simple. All right, so we'll stop there.